Greetings! The following is part of a series of lectures on black holes. In this particular lecture, we will try to gain a more robust understanding of particle motion in Schwarzschild spacetime. The outline of this lecture is as follows. First, we will give a brief summary of what we have learned in the last lecture. Then, we will derive the conserved quantities and write the radial equation of motion for Schwarzschild spacetime. Finally, we will derive the capture cross-sections for massless particles and non-relativistic massive particles. In the last lecture, we learned how to draw Kruskal-Szekeres diagrams and Penrose-Carter diagrams for Schwarzschild spacetime. In this diagram here, the horizontal axis is the capital X axis and the vertical axis is the capital T axis. We can see from the blue lines that lines of constant small r are hyperbolic, and from the gray lines, lines of constant small t are linear. Moreover, we can see from the zigzag line, this represents the curvature singularity, and it is a hyperbola. This hyperbola has the equation u times v equals 2m. In addition to this, we can see that u times v equals 0 corresponds to these two lines, which correspond to the event horizons, and thus divide spacetime into 4 regions. However, there is one downside to Kruskal-Szekeres diagram, is that it has infinite range. For a better visualization, one can perform a conformal transformation to map the Kruskal-Szekeres diagram to a finite range, namely the Penrose-Carter diagram. Here, in this diagram, the x tilde and t tilde axes are the horizontal and vertical axes, respectively. We can see from the figure the blue lines correspond to lines of constant small r, and the gray lines correspond to lines of constant small t. Notice that this is very similar to the Penrose-Carter diagram of Minkowski space, but the top and bottom triangles have been chopped off. This is because there are singularities at those points. The event horizon corresponds to lines of capital T tilde equals capital X tilde and capital T tilde equals minus capital X tilde, or in capital U tilde, capital V tilde coordinates, capital U tilde equals 0 and capital V tilde equals 0. The zigzag line again corresponds to the singularity, and as mentioned before, this should be a hyperbola, but we can always multiply by a conformal factor to make it straight. As we can see from this Penrose-Carter diagram, it is divided into 4 regions. Region 1 is known as the exterior black hole region, where capital U tilde is less than 0 and capital V tilde is greater than 0. Region 2 is known as the interior black hole region, where capital U tilde is greater than 0 and capital V tilde is greater than 0. Region 3 is known as the exterior white hole region, where capital U tilde is greater than 0 and capital V tilde is less than 0. And finally, we have the region 4, known as the interior white hole region, where capital U tilde is less than 0 and capital V tilde is less than 0. Now, the objective of this lecture is to understand the geodesic of particles in Schwarzschild spacetime. One way to do this is to directly solve the Euler-Lagrange equation to obtain the geodesic equations. Then one can use a computer to solve the angular and radial equations of motion. However, this process is rather tedious and does not provide the reader with a deeper understanding of the Schwarzschild geodesics. Instead, we can make use of conserved quantities to not only make life easier, but to provide the reader with a richer understanding of particle motion in Schwarzschild spacetime. Recall that the Schwarzschild metric in Eddington-Finkelstein coordinates is as follows. Therefore, the Lagrangian can be written in the following manner, where V is written as so to save writing, and the overdot is to represent a derivative with respect to proper time. For the sake of simplicity, let us focus on the radial motion of the particle in Schwarzschild spacetime. To simplify the model, let's consider a particle moving in the equatorial plane, that is set theta equal to pi over 2. Usually, one would like to choose a plane such that the velocity of the particle will always remain in the plane. Doing so, we find that theta dot is equal to 0, and thus the Lagrangian reduces to the following form. As we can see, the Lagrangian is independent of v and phi, and therefore have some conservation properties. We can see from the Euler-Lagrange equation, setting v as the coordinate, we find that the quantity inside the bracket is a constant and it's therefore conserved. We can name it E as it is the energy per unit mass. Similarly, using the Euler-Lagrange equation for the coordinate phi, we find that this quantity in this bracket is a constant and is also conserved. Therefore, we can label it L, as it is the angular momentum per unit mass. Moreover, the metric compatibility implies that along the path, the quantity epsilon is a constant. For massive particles, epsilon is equal to -1, and for massless particles, epsilon is equal to 0. And using these conservation laws, we find that v dot is equal to r dot minus E over v, and therefore the radial equation of motion is as follows. Simplifying the above expression, we yield the following. This equation may seem to look nice, but it is actually still very difficult to solve. One would need to use elliptic functions to get an analytic solution to this. So instead of doing some horrible integrals, there is a simple trick to develop intuition and understand the motion of the particle. Recall that in classical mechanics, it is easier to analyze equations involving derivatives with respect to angular coordinates rather than equations involving derivatives with respect to time. To simplify this, we can make a substitution r equals 2m over u, and therefore r dot is the following. Performing this substitution, we obtain the following expression, which is the radial equation of motion. With this, we are ready to derive the capture cross-section of both massless and massive particles in Schwarzschild spacetime. First, let us write equation 3.2 in the following manner. The first term on the left-hand side of equation 4.1 is analogous to the kinetic energy. The second term, third term, and fourth term on the left-hand side of equation 4.1 are analogous to the potential energy, and the term on the right-hand side of equation 4.1 is analogous to the total energy. Recall, for massless particles, epsilon is equal to 0, and therefore the potential energy is as follows. Taking the derivative of the potential energy, and setting it to 0, we find the maximum. Therefore, we find the maximum has two solutions, one at u equals 0, which is dull, and the other at u equals 2 over 3. Substituting this back into the equation for r, we find that r is equal to 3m, and therefore we have discovered that light can orbit a black hole at radius r equals 3m. One will notice that this point r equals 3m is unstable, so a qualitative understanding can come from just drawing a picture of the potential energy. As we can see from this potential energy, if one perturbs the particle to the left, the massless particle would escape to infinity. However, at the maximum, if one perturbs the particle to the right, u would increase without bound. Thus, r would decrease without bound, so the particle would fall into the black hole inevitably. Now, to calculate the capture cross-section, we need the energy at r to infinity. Doing so, we find that E is approximately equal to minus T dot. And now, consider the case where the total energy is greater than the maximum potential energy. If the inequality in equation 4.4 is satisfied, the massless particle will be absorbed into the black hole. Now, recall that capital U has a maxima at small u equals 2 over 3, and therefore U max is equal to 2 over 27, and therefore we have the following inequality. Now, if the inequality from the previous slide is satisfied, the massless particle will be absorbed into the black hole. Now, let B be some impact parameter. Therefore, if we write L in terms of the impact parameter in the following manner, we obtain the impact parameter for which the massless particle will be absorbed into the black hole, namely B equals 3√3 m. And since the capture cross-section is defined as pi b squared, the capture cross-section of a massless particle in a Schwarzschild background is 27 pi m squared. Now, we can do the same for massive particles. To do this for massive particles, we have to consider three cases. The first case is is, wait, okay. Actually, we can always do this calculation for relativistic massive particles, but this is a little bit beyond the scope of this lecture. But it can be done, but the calculation is just a little bit more tedious. For non-relativistic particles, we have to consider three cases. The potential energy in three scenarios. When the term 2m squared over L squared is small, the contribution of this term does not make a huge difference, and thus the potential energy will look like the following. Thus, the maxima occurs when the value of the potential is positive. As we increase the term 2m squared over L squared, the height of the maxima decreases. And in this second scenario, we can get a curve where the 2m squared over L squared is large enough such that the maxima occurs when the value of the potential is negative. If we further increase the term 2m squared over L squared, we can yield a curve with no turning points. In the case of massive particles, E is approximately equal to minus t dot. Therefore, we know that E is equal to 1 over gamma, where gamma is the gamma factor. This is because out at r to infinity, one will get Minkowski's flat space, and thus the rules of special relativity will hold. Now, expanding capital E for small values of V yields the following, and doing the same for capital E squared yields the following, and thus we obtain the following expression for the total energy. Now, recall that the potential energy for a massive particle in Schwarzschild spacetime is as follows. The dividing line which the maxima of the potential energy is below 0 occurs at U max equals 0 and U prime equals 0. Therefore, we have the following simultaneous equation. Solving the above would yield U equals 0 and U equals a half. And substituting this back into the equation for the captured cross-section, we yield the following. Therefore, the impact parameter for a black hole to capture a massive non-relativistic particle is B equals 4m over V. And thus, the captured cross-section is equal to 16 pi m squared over V squared. I hope you've learned something in this lecture, and see you in the next one. Thank you.